short. We went through a lot of the Chapter 11 homework today. The key with this is making sure you understand the information that's giving and how it relates to the idea of thermal energy and efficiency. So we've got, for problem 4, I think we went over in class, we've got a dam which has 690 cubic meters per second flowing at 220 meter vertical distance. So what we can do is we can get the kinetic energy that you would get from that, from the gravitational energy, by multiplying mgh. And since they're asking for power, we're going to do that per second, because it said it was 690 cubic meters per second. So that gives us a certain number of joules. But it said that the turbines were only 90% efficient. So we multiply that by 0.9, and that gives us our power production of 1.3 times 10 to the 9th watts, or 1,340 megawatts. Problem 5. The input is 1 watt, it's 20% efficient, so the output of each bulb is only 0.2 watts. So therefore you'll need 8 of them to get 1.6, and that'd be 8 watts of input. For problem 32, this was the fan going in the room for an hour. I was asking how much thermal energy was added. So really all that initial energy input is eventually into thermal energy if it's a closed system. So I just multiply the power rating by the time that the object's moving, or the time the object's on, and that gets me 432,000 joules. 33 is looking at what's happening with the internal energy. So if you have 600 joules of heat coming in and 400 joules done as work, you have a change in thermal energy of plus 200 joules, so this thing would warm up. 34, the scuba tank. If it keeps a constant temperature, you've got work flowing in from the air being compressed, and heat flowing out into the water, which is outside the scuba tank. So the delta U would have to be 0 because there is no change in temperature. 35, I hope you like my drawing. It's a piston pushing down, plus 20 joules of work is being done. We know it's positive because the system is being compressed or squished. 10 joules of heat energy is removed, so that means you have an internal energy of change, or thermal energy change, of plus 10 joules, so the temperature will increase. 39, the key thing is I had to convert to Kelvin first. So it gave me a hot and cold temperature, but to get my efficiency I had to convert that to 293 Kelvin and 873 Kelvin. The maximum possible efficiency was 66.4%, but it said that we got 30% of that, so that's 0.199 or 19.9%. So therefore, if I've got a 19.9% efficiency, I ended up getting 1,000 joules out. I have to put a little over 5,000 joules in. 43, again, got to convert to Kelvin, so end up getting a 47% maximum efficiency based on this efficiency equation, and then thinking about the what you get for what you pay, that's a 35% actual efficiency. 52 is similar to an example that I did in class. So we've got the first one violates the second law because you end up having a greater efficiency, which is 60% here, than you're allowed to. So the temperature difference is 2 to 1, so you can't have more than 50% of the energy used. You have to have at least 50% go into the cold reservoir. For part B, we have 10 joules coming in, but 11 joules going out, so that violates the first law. And the third one, part C, is fine. We have 30 joules coming in, 30 joules going out, so we don't violate the first law, and we have a 33% efficiency, which is below the 50% maximum that we could calculate, which is true for A, B, and C. For number 64, so we've got work done as 10 joules. The output plus waste heat would equal 15 joules, so the input had to be 25 joules. So the waste heat, was the 15 joules. So I ended up having a 40% efficiency in that particular case. For part B, got a cold temperature of 293 Kelvin. So the maximum efficiency there was 40%, so I have to work backwards and figure out my hot temperature. That's 488 Kelvin. So it's kind of rearranging this formula, and that's 215 Celsius. And I think I left 66 off, so I'm not sure if I even did that correctly. I'll have to talk to you about that in class. Thanks.